Let us look at the example 2.21. So for fuzzy Cartesian. So suppose that there are two universe of discourses, that is x is equal to mn, and another universe of discourse y is equal to pqr. And we have two fuzzy sets A and B that are defined on them. So this is the value of the fuzzy set. You can see the fuzzy set A contains the elements m and m with a membership value of m has 0.3 and n has 0.7. So this can, we have already seen that this is one way of representing a fuzzy set, where this value shows the element and this one shows the membership value, that is mu of m. Okay, so you can either write it this way, or you can also write it as m comma 0.3. That is one element in the set. Another element is n comma 0.7. So this way also you can represent it. Okay, a fuzzy set A. Now this is a fuzzy set B with PQR, the membership values 0.5, 0.1 and 0.8 respectively. Now suppose that I'm asking you to find the Cartesian product of A and B, that is the membership value, uh, over the Cartesian product A and B. We need to find what is the Cartesian product for the values, that is, say, take the first value, m comma p. Okay, so what happens here is, we know that for finding this value, we have to find the minimum of among both the membership values of each of the element m as well as p. So we find with this is the equation that you're going to use, that is minimum of membership value of m that belongs to the fuzzy set A, and membership value of p that belongs to the fuzzy set B. So you have to find the minimum. So let us look at what is the membership value of m. That is, you can see here it is 0.3 and the membership value of this is 0.5. So minimum of 0.3 and 0.5 gives you 0.3. So that is what, after finding the Cartesian product of A and B, for m and p, the value or the answer that we get is 0.3. Okay, but when we look at the values m and q, okay, so m and q, so we are going to take this value m and we're going to take the other element q from the set B. So the membership value of this one is 0.3 and 0.1. So finding the minimum of 0.3 and 0.1, we get the answer as 0.1, and that is what is defined here, shown here. So you can see the membership value of all the other elements of the fuzzy Cartesian product of A and B can also be found in the similar value. So you take another value, say n. I'm taking another value, say n. So taking n with p, n with q, and n and r. So in order to do that, we have to find out what is the minimum among 0.7 and 0.5. So it is 0.5 that is shown here. Then what is the minimum among 0.7 and 0.1? That is 0.1 that is shown here. Then 0.7 and 0.8. So you can see that is 0.7, again the minimum. So that is why we got the answer as 0.7 there. So this can be, these are the values we got. If you write it like this, according to the equation, you get the value like this. But we can also show it in the form of a relation matrix that is like this. So we, on the one row wise, we write m and n, and column wise, we write the other elements, that is PQR, and we show the relation between them. What is the relation of m and p in the Cartesian product of A cross B? Okay. So basically a fuzzy relation R between two fuzzy sets A and B. So you can say if this is any relation that you take from among this Cartesian product is basically a subset of the fuzzy Cartesian product A cross B. That is, you can say R will be a subset of A cross B. So if you're trying to find out a relationship between from among the Cartesian, it should always be a subset of the set A cross B. Okay, because the Cartesian product, fuzzy Cartesian product A cross B. So you can see A cross B is a fuzzy Cartesian product of the set A and B. We already know that. So the fuzzy, when it is called a fuzzy relation, because we already found this, and from among that we are trying to find a relation. So this has to be a subset. As another example that is shown here, and this is also another relationship property. We'll come to that now. So suppose that you have a fuzzy set. This is another example. So you can see here, you have a fuzzy set A and a fuzzy set B on the universe of discourse X and Y. So you can say fuzzy set membership value of each element X that belongs to the universe of discourse capital X on the fuzzy set A, the membership value is given here, and mu of y for the fuzzy set B, where y belongs to the universe of viscose capital Y. So we can say a relation is A cross B is Cartesian product. It's a subset of the Cartesian product of the universe of viscose, that is X cross Y. So then the relation will have its membership value given as like this. So mu R of XY for the elements XY is nothing but mu of A cross B of XY, which is nothing but minimum of mu of X of the set A and mu of Y of the set B. Okay, so mu R of XY is nothing but the relation A cross B, that is the Cartesian product, which is nothing but the mu A of X and mu B of Y, and we take the minimum among both of them. So as an example, just like we did before, we can write this in this representation also, 0.7 by A2 and so on. This indicates that this is the element and this is the membership, and these all are the different elements. So we can also write it in a set format like this. So this is how it looks like. So we'll look at the method given here. So A1 is the element in capital A, which membership value 0.2, A2 has 0.7, A3 has 0.4. Similarly, you have a set B. Now, in order to find the relation, that is a Cartesian product, you can see here, we write it in the relation format and in relation matrix format A1, A2, A3 and B1, B2. These are the elements, right? So B1, B2. So you have to find the minimum of each element. Say you take first element from the set membership value of the first element in A and membership value of another element in B. So suppose I'm taking A1 and I'm taking B1. Okay, so from the first one I'm taking A1 and the second one I'm taking B1. So what is the membership value here? 0.2, and here it is 0.5. So which is the minimum among 0.2 and 0.5 is nothing but 0.2. And hence you got from A1 to B1, the relationship value will be 0.2. Similarly, we'll be taking for 0.2 and 0.6. So again, it will be 0.2. Now we'll move on to the next value element in set A, that is another value X and another value Y we need. So suppose here it is A2. So we'll be checking with 0.7 and 0.5. 0.5 is the minimum. Again, 0.7 and 0.6. 0.6 is the minimum, and so on. Whereas in the third one, 0.4 is lesser than 0.5 and 0.6. So both the answers are 0.4. So this is another example. Okay. Now you can see here, we consider, just a second. Okay, we consider a fuzzy sets A and B cited in example 2.21. That is in the prescribed textbook, you have 2.21 as this one. That is A and B were given and we had Mn and PQR. So if you're looking at this example and their Cartesian products, okay. Now what they have described here is the relation matrix gives below a subset of the Cartesian product of A cross B. So this is another relation matrix. This is not the relation matrix that you saw here. This is the Cartesian product of that. Okay, this is the Cartesian product. And we are showing another relation here, which is a subset of this Cartesian product. So you have another relation R, which is a subset of the Cartesian product. For all X that belongs to the universe of viscose capital X, and similarly another universe of viscose capital Y. So you can say that mu R of XY, okay, membership value of a relation for the elements XY will be less than equal to membership value in the Cartesian product A cross B for the same XY. So therefore, R is a fuzzy relation between the fuzzy sets A and B. So you can see the value here is something different. Somehow we found out this value. And here you can see it is 0.3, 0.1, 0.2, 0.5, 0.1, and 0.7. But here it is, you can see all the values are lesser than the Cartesian product. So it is a subset of that. Okay. Now suppose we take another matrix R dash or another relation R dash. Now when you look at this example, when you compare it with the value that is available in the original Cartesian product, so I'll just erase this. You can see it is 0.3, 0.1, and 0.3. And we look at the values if they are less or not. So here it is 0.2, which is less than 0.3, so it's okay. The second value in the original Cartesian product was 0.1. That is M. The relation M and Q was, you can see here, it is 0.1. But whereas the value that we have here is 0.3. We can see 0.3 is greater than 0.1. So how can it be a subset? Isn't it? So for the value M and Q, this value stands greater than the original Cartesian product. So you can say that R dash is not a fuzzy relation between the fuzzy sets A and B. Only if all the values are, you can say, lesser than or equal. This is a property. It's lesser than or equal to the Cartesian product. Then only you can say it is a relation. It is a fuzzy relation between the fuzzy sets A and B. Now, what are the different operations that can be done on two fuzzy relations? So earlier we learned how to do different operations on fuzzy set as well as crisp set, etc. Now we are going to look at how operations can be done between two fuzzy relations. So like before, we know all the operations: union, intersection, complement, composition. We have learned this in the crisp set. So now we look at the same thing for fuzzy set. So mu of R union S over the elements A, B is nothing but max of the membership value of R, comma, the membership value in S. Okay. So for the relation, when you talk of relation, you will have two entities, right? Then only it can be a relation. So the relation in of A and B, the membership value for A and B, and for A and B elements, the pair of elements, ordered pair of element A and B, what is the membership value in the set S, in the relation matrix S? So we'll be looking at these two and we find the maximum, and that will be the union of that. Similarly, intersection. Mu R A B, mu S A B, the minimum of them will be the intersection of the result of the intersection. Similarly, we have another property, that is our operation, that is complement. It is nothing but, if you want to find for the relation R, then it will be mu R of 1 minus mu R of AB, which is denoted by R dash. Okay. Similarly, we also have an important property, that is composition. So it is denoted by R, this operator, and S. So this is known as the composition operator. Now suppose it gives you a new relation matrix T. So it is basically of two types. I already told you, that is the max min composition and the max product composition. So we'll look at each one of them. In the crisp set, we learn what is the max min composition, where you have two relations and we find the first row and the first column of the other matrix. We find what is the minimum among all of them, and then we find the maximum among all the three, or all the elements that we found. So this way we have a max min composition, and also similarly we have another one, that is a max product composition. Okay. Now the same thing, but on a different slide, from a different, that is from the original textbook. I put this image here. So union, I already told you, it's the maximum, intersection is the minimum, and the other one is 1 minus. Other than these three common relations, we also have something known as inclusion, dominance, and equality. So you can see inclusion. R is a subset if elements in R is less than S. It is a superset if it is greater than equal to. It is equal when the values are equal, and we can also have properties like this. Okay. So composition is the max min composition that we looked at, and we also have the max product. So max min, the definition is given here, that A, B, and C be three crisp sets. R and S are fuzzy relations over the Cartesian product of A and B and C respectively. So R is a relation over A cross B, and S is a relation over B cross C. So we are pairing the first two and then the second and the third. Now max min composition of R and S, denoted by R operator, this operator round dot operator S, is a relation over A cross B. So you can see the common entity here is B. So we are trying to find a relation of A cross B such that you can see it is the minimum of the membership value of R and the membership value of S, and then finding the maximum of this. So you can see in the first set we have got X and Y, and in the second set we have got Y and Z, where Y is the common factor which belongs to the set B. Okay. So what we are trying to find out here is not actually Y and X and Y, it should be, sorry, it should be X and Z. Okay. So the composition will be X and Z. Now we'll look at an example of a max-min composition. So suppose that we have a set A, ABC, B with elements XY, and C with elements PQR. There are three crisp sets. Now we are going to define two fuzzy relations R and S that are defined over A cross B and B cross C respectively. Now the relation matrices of R and S are given by these matrices shown here. So you can see we have described all the elements. That is the first set of elements are A, B, C here described here, and in B we have described it here. The same thing B here comes in the rows, and for the element C, for the set C, the crisp set C, the elements are defined on as columns P, Q, R. Okay. Now we have to find out. So suppose this is just finding out the composition. Actually, we have left out how union, intersection, complement, etc. can be done. I'll show you an example for that also. But in order to, can we do a union of R and S here? No, it is not possible. Why? Because the matrix size is different. Because if we have to do a union, the matrix should visually, you can say it should look something like this itself. It should have ABC and XY. It should be over the same set of elements. Then only you can do union, intersection. Then only we can do these two operations. Okay, complement we can find out. So, but this is finding out the composition where you have a common entity, that is this particular element or the set B, which is a common factor in both the relations. So when you have the same, the number of columns here and the number of rows here will have the, you can say the same size, then we'll be able to find the composition of this. Okay. So what you have to do is we have to find the composition of R composition S, that is a min-max composition, which is defined on the Cartesian product of A cross B, A cross C, sorry. So the entire thing is defined. We have the relation A cross B, and we also have the relation B cross C. Now we are going to find a Cartesian product A cross C, and we are trying to find a new composition R, composition X, and that is nothing but a max-min composition. Now suppose we'll take the first set of elements here. Let us take this. We'll take the first element here, A, and we'll look at the, you know, this is the elements of matrix A. These are the elements of matrix B. These are the elements of matrix B, and these are the elements of matrix C. Now we are going to find A cross C, right? So we are going to take this one and this one. Okay, so that is what we are showing here. So our composition of A comma P, what will be the, it's a max-min composition. So we have to find, we have to go through this row and this column. Okay, so we have to find the composition of A, that is R of this for A cross B will be nothing but maximum of, you can say min of what, 0.3 and 0.4. Got it? 0.3 and 0.4. And it is nothing but minimum of 0.7 and 0.3. So this way we have to find out. So the minimum of 0.3 and 0.4 is 0.3. The minimum of 0.7 and 0.3 is 0.3. Now what is the maximum of this is nothing but 0.3. Okay. So the relation T, that is nothing but R composition S, will be a matrix like this, where the first value will be 0.3. Okay, you can see the answer here. It is shown. The answer here is 0.3. So the first value, remember, you will have something like this: A, B, C, and this element C has three elements. So this is the matrix. Sorry, this is the fuzzy set A, and you have another fuzzy set C, which contains three elements P, Q, and R. So this is what we are trying to solve. Okay. Now let us look at the second value that is to be obtained here. So we have got this row and this column. That is the element A and Q. That is what you're trying to find out. So the element A means the row that is contained here, and Q means the column that is contained here. So we have to find the minimum of 0.3 and 0.1. What is that? 0.3 and 0.1. That is 0.3 and 0.1 is, so I will write here Q. 0.3 and 0.1 is the first element, and then you have got 0.7 and 0.7 again. Now the minimum here is 0.1 and 0.7. Now the maximum of 0.1 and 0.7 is, we'll change this and put it 0.7. So the value here will be 0.7. See if it is correct. Yes, it is 0.7. Okay, and so on. So this way we find out for each of the set of elements in the row and column, and we can write it in this format: minimum of R of AX of XP and AY and YP, and we find the minimum values, and then we find the maximum values, and so on. This way you can do it. You can show one or two while you write the answer. You can show one or two examples like this, and then if you can do it in your mind, you can just finally write down the answer, or the entire relation can be calculated and written fast. Okay. Now this is another example of the same min-max. You can check it out as an as a homework. Here also you can see there are three universe of discourses: X, Y, and Z. Maybe a crisp set, and the relations are fuzzy relations are shown here. So between the set X and the set Y, and between the set Y and the set Z. So we have to find the pair for, that is the R composition X on X and Z. Okay, so we take each one, X1 Z1 we find out, then we find out X2 Z1, X3 Z1, X1 Z2, X1 Z3, and so on. So for each of the rows and columns, for every X and Z, we'll find out the max-min composition. Okay, now we'll look at what is, there's one more example given here of a max-min composition. We'll look at that, and then we'll look at max product. So consider this, such type of questions can be asked. Maybe directly we won't ask what is the max-min. So they can give you some questions like this, and eventually you have to find the composition. Say, suppose that you have a set P and D, which represents a set of paddy plants and a set of plant diseases. So P represents the different kinds of paddy plants, P1, P2, P3, P4, and D represents the plant diseases, D1, D2, D3, P4. So you have four varieties of such plants and four diseases that affects these plants. Now we also have another set S1 to S4, which are the common symptoms of these diseases. So you have three sets here, right? Now let R be a relation on the Cartesian product of P and D, okay, representing the plant is susceptible to diseases, where R can be stated like this. So for each type of plant, what is the strength of how it can be affected from the disease? So you can say P1 is greatly affected by the disease D3, the disease named D3, and 0.8 has another value is 0.8. So the disease D4 and D3 greatly affects P1, okay, than the other two. Similarly, you can see the plant P2 is least affected by the disease D1 and is the most affected by the disease D3, and so on. So these fuzzy values show the strength of the plants and their corresponding diseases. Now, this is not enough. So what we are going to do is we are going to have another relation that we can find the composition. Now, they should have a common factor, that is the disease. So TB, so this is one relation. Now let not T, S be another relation on, or because we already have a S, I think it's better to name is T, and we'll find out, maybe put a T here. We already have a set named S, right? So let us put a T here. Okay. Now let T be another relation on D cross S. So it will be, that is, what is S? S is the symptoms, right? So for a disease, what is the symptom that it shows? Say you have four kinds of symptoms. Okay, say leaf will rot or root will rot or something like that. So for each disease, this symptom, the strength of the symptom will be high. That indicates that this is the kind of disease the plant is affected from. So you can say similarly for every other disease, what are the different symptoms and what are its fuzzy strengths. So now, well, the question is, obtain the association of plants with different symptoms of the diseases using a max-min composition. So they'll ask you to verify, how do you find out? So we had a relation from plant to disease, and we had a relation from disease to symptom. Now what they're trying to find out is What is the association of the plant with different kinds of symptoms? So the question is, we have to find out Cartesian product, the relation between over the Cartesian product P and S. So that can be only done with the help of a max-min composition. Okay, so we have to find. So the same thing, we learned this before. We had matrix A and B, and then we had B and C. So we had to find out the relation between A and C. The same thing is mentioned here. So in order to find out R composition T, okay, so this is T, R composition T, then we have to find out that and we can verify. So R composition C, what do you have to do? You have to take the first row like this, say minimum of 0.6 and 0.1 over here. Then minimum of the second value 0.6 and you can say 0.2 here. Then the minimum of 0.9 and 0.7. Then minimum of here 0.8 and 0.9. So we'll find out the minimum among all of them. Okay. So and then we have to find the maximum. So the output that we get will be 0.1, 0.2, then 0.7 and 0.8. So from all the values, 0.8 is the maximum. Then you have to find the maximum, right? So we get the maximum as 0.8. So find out the minimums among both the, oh, sorry. I took the wrong, I had to take the column here and I took wrongly, I took the row. So please ignore what I said. You take the first row and you take the first column, right? So among that, when you find out, you can see that 0.8 eventually will be the maximum on this. So you don't have to, so just ignore what I said before. You can just delete all this and you have to find the minimum among this row P1 and the column, because symptom is not denoted as row, symptom is denoted as a column. So we need to take the row here and the column here. Okay, so you have to find out, I'll repeat again, you have to find the minimum among 0.6 and 0.1, which is 0.1. Okay, then you have to find the minimum among 0.6 and 1, which is 0.6. Then minimum among this row, that is the third element, 0.9 and 0, which is 0. And then you have 0.8 and 0.9, which is 0.8. So among all of these, which is the maximum, 0.8. So that is how we got this. In the earlier case also, we got the same answer by mistake, but this is the correct procedure. Now, what you have to do to find the second value, say P1 and S2, what we have to do? We have to take the same row, this elements itself, and we have to take the second column. Okay, so this is how we do it. So finally, you get an answer like this. So a similar question is there in our syllabus. If you have seen, there's given a sample question paper where a similar question with different like colors and something like that is given. So this is all of such examples which will give you three sets of elements like P, D, and S, and then they show a relation between the first two and the second two. And eventually, you will be able to find the relation between the first and the third one. So that is a max-min composition. So this is basically the a set a bipartite graph representation. So that these are the three sets. This shows how the relation is mapped and how the relation is mapped between. Now, what are we trying to find out? We are trying to find a relation directly from X to Z. That is what we are trying to find out in a max-min composition. This max-min composition can also be written in like this. We know that finding the min is nothing but finding an intersection. This is the representation for intersection. And finding the max is nothing but finding the union among two elements. Okay, so we can also represent the question comes like this. You can see that one is the intersection and one is the union. Another way of instead of writing in detail, you can also write it in a short form notation like this. You list down both the matrices R and S. Okay, and you take the first row here and the first column here. Write down all the elements like this. So this is the yellow one shows the row here, and the blue one is the column here. We are writing it like this. Now find the minimum among this. Okay, so the minimum is 0.1, so we write it down like this. Here it is 0.2, we write it down here. Here it is 0, so we write it here. And here it is 0.4, so we write it here. Now find the max of all these elements. And that is what we write here as the answer. Okay, so here you have the elements 1, 2, 3, A, B, C, D, and A, B, C, D, and alpha, beta, gamma. So you can see The elements 1, 2, 3 and alpha, beta, gamma are written for the relation for the composition R, composition F, and this is the answer you get as a first step. So this way also you can quickly calculate. Just a hint for or another way of doing it. It's the same thing. Now we'll look at what is the max product composition, another type of composition where we find it's given, you can see the name itself shows it is max. Earlier it was max and min, but now it is product. So all of you know what is meant by product. So the membership value of a particular element in relation R and the membership value of a particular pair of element in the relation S, we take, there's a dot operator here, we take the product here. Okay, so you find the product of these two elements and then find the maximum. That is all. So I'll just write the equation once again. It is given by, for any relation R mu R composition S, for the elements X, I'm writing it in relation to what we learned for max min composition. The similar terms are used here because this is taken from another set of example. You have different naming here like X, V, V, Y, etc. So we'll be looking at X, Y, and Z, right? Three sets. So for the relation between X and Z can be shown as mu of R composition X, X comma Z is nothing but max of mu of relation R on X comma Y into mu of S into Y comma Z for all Y that belongs to the universe of discourse capital Y. This is the basic idea. Or you can also write it as, another notation is R composition X of S of X comma Z is nothing but the union of, for all Y that belongs to capital Y, of mu R X comma Y product of mu S Y comma Z. So this way also you can write. Like we had a different notation here with the union and intersection that you saw here. The same thing is done here also. Here we do not have the intersection. Instead we have the product and then we take the maximum of that. So we look at one example. You'll understand it better. Say this is a relation 1, 2, 3 and ABCD and ABCD and alpha, beta, gamma. So for finding the max product, what you have to do is you take the same way. You take the first row of this and the first column of this. You find the product between each of the elements. Earlier, we used to take the minimum of 0.1 and 0.9. Here, we're going to find the product. So 0.1 and 0.9 is written parallelly and we find the product that is 0.09. Then find the product between 0.2 and 0.2, the second elements in each, and you found it as 0.04. Then 0 and 0.8, that is nothing but a 0. So that is what is shown here. Then you have a 1 and a 0.4. So the product of this is 0.4. Now find the maximum among all the four. So the maximum of all the four is 0.4. Okay, this is 0.04, 0.9 and 0. So naturally 0.4 is the largest. So 0.4 is a relation between 1 and alpha. Okay, so this is known as max product. This the same method could have been done in XSpec, but we did not look into that because the same procedure is done. So this is how we do max product composition on a fuzzy set. Okay. Now, what is another topic? So that was all about different properties on fuzzy sets. What are the operations that can be done, etc. Now we look at something known as the alpha cut set. What is meant by the term alpha cut set? So an alpha cut set, A alpha. Okay, it's a set. It's basically a crisp set. Okay, alpha cut set is a crisp set. It is actually made up of members whose membership is not less than alpha, where alpha is any arbitrary value. You can take any arbitrary value from among the existing values that are there. You take any arbitrary value and we find out a new set known as A alpha. Now, what is A alpha? A alpha, where alpha is any value. Okay, you just have to find out the values of X whose membership, the values of X has to be written. Value of X means the direct crisp values like 15, 25, 35, etc. The values of X that belongs to the universe of discourse capital X where the membership value of that element should be greater than or equal to a particular value alpha. Okay, the membership value of that particular element should be greater than alpha. So an example can be shown here. So in order to understand this example 1.1, we need to have a background. So this is the example 1.10, where you have a universal set X with values 5, 15, 25, etc. till 85. This is basically age of a person. So we have seen this example before in the previous classes. So if age of a person varies from 5 to 85, we are classifying it as different fuzzy sets named infant, young, adult, and senior. Okay. Now, infants are not in any category, so all the memberships were zero. Young, for age 5, the membership value is zero, but for 15, it is 0.2. For 25, it is complete membership 1. 35 it is 0.8, and it reduces, and so on. And you can see adult also, there's some membership value. And then for senior citizens, you have some membership values that goes from here, from here till here. Okay, and so on. So but these does not have any membership value, these age groups. So these are, this is a fuzzy set that has been described for these universe of discourse of ages from 5 till 85. Now, what is the alpha cut? So alpha cut is derived from the fuzzy set young by giving 0.2 to alpha. Suppose I give a value 0.2. You know there are many fuzzy values here. Suppose I'm taking alpha as 0.2. Now I want to find the alpha cut of the fuzzy set young. Alpha cut of the fuzzy set young. Okay, so what is the definition of alpha cut? We just looked into for any element x. X means what? The ages 5, 15, 25, etc. Okay, for any element x, the mu of x means the membership of x, it should be greater than 0.2, greater than or equal to 0.2. So for all the values that are greater than 0.2, you can include it into this set. Now let us look at all the values that are greater than 0.5 in the fuzzy group young. Okay. Now you can say which are the values that are greater than which are the elements x that has a value greater or equal to 0.2. So you can see all these elements, yeah, till here. Okay, these elements. That is for the x value 15, 25 has a value of 1, 35 has a value of 0.8, which is also greater than 0.2. 45 has a value of 0.4, which is also greater than 0.2. But this is a value 0.1, which is lesser. This is lesser, the lesser, and lesser. And even this one is less. So we have only these age groups, right? That has a alpha value greater than 0.2. So there's a mistake here. The young of 0.2 contains these many elements: 15, 25, 35, and 45. So when you write young of 0.2 means this is the value alpha we have currently taken. So what does this mean? This means that the age that we can say youth with possibility not less than 0.2. So nothing lesser than 0.2 values are not taken. We can say these are the age groups which for values greater than 0.2. So suppose the alpha value was 0.4, which would have been the age groups. So you can look at here for values greater than 0.4. So which are the values greater than 0.4? This is there, this is there, this is there. That's all. Only three values. That is 25, 35, and 45. And that is the answer that is given. It's another crisp set with young of 0.4. Similarly, when alpha is 0.8, young of 0.8, the only two elements are there, 25 and 35. So when two cut sets A alpha and A alpha dash exist, if alpha is less than equal to alpha dash, then we can say that A alpha will be a superset of, okay, A alpha will be a superset of A alpha dash. So you can say that young of 0.2 has more elements. Naturally, you can see here young of 0.2 has more elements than young of 0.8 because young of 0.8 is 25 and 35 only. And when we had a lesser value, we know that 0.2 is lesser than 0.8. So we will have more elements here because 0.8 is by naturally comes, it is greater than 0.2. So all the elements in 0.2, some of them will fall in the category 0.8. Okay, so this example will hold. Now, there's also something, so this is a basic definition of a alpha cut, just repeating it once again. It's a crisp set whose elements have at least alpha degree of membership in the fuzzy set A. So you should have at least alpha degree. So if it is 0.2, all the membership values should be at least 0.2 and greater than. Okay, so you have to write down the elements here. Now, in contrast to this, you have something known as a level set. Now, what is a level set? The value alpha, which explicitly shows the value of the membership function, should be in the range of 0 to 1. That is why it is a fuzzy set, right? All the values will have the values between 0 and 1. So, level set is actually obtained by the alphas, the alpha values. So, you just have to find out for all alphas that are greater than equal to 0. That is, you should have minimum 0 and greater than that. So, for all the positive values, so that is greater than 0. If the membership value of that element is alpha, then you just write that alpha. Okay, so for all the values greater than equal to 0, alpha values greater than equal to 0, you just need to list out the elements, the fuzzy membership values, mu values. Okay, just list out the mu values of each element x in the set A. So what are the the maximum possible alpha values? That is the basic meaning of this. We had an alpha value 0, we had an alpha value 0.1, 0.2, 0.4, 0.8, and 1. You can see, look at this table. Those are the values that we have in the young set. We had 0.2, we have a 0, we have a 0.8, we have a 0.4, we have a 0.1, and so on. So what are the different possibilities? And there's also a 1. Yeah, 1 is also there. So all the values between 0 and 1, which can take on the value alpha, that alpha values are written here, and that is known as a level set. But whereas in an alpha cut set, we write the age groups, the crisp values were written. But here the fuzzy membership values are written. That is a difference. Okay, so that is all.